lecture VH7, and we shall continue with a mathematical formalization of complex networks, of complex network dynamics. This is some content that usually is difficult for some of you in the past, for your colleagues. It has been difficult to understand, so please pay attention. We'll look for a description of spreading phenomena within complex networks. This can go from the spreading of viruses like COVID, or the spreading of opinion, and within a network. And as we have seen, we can describe projects and processes as networks, and we are going to investigate the spreading of cpDNA and dcPNA within organizations. Okay, so basically we want to understand how mathematically how the spreading of certain behaviors takes place in socio-technical environment. So we have seen we deal with a socio and technical. Let me paint it beautiful. We have seen how we are moving in a socio-technical world with two dimensions: social with trust and trustworthiness and stuff, technical here, and now we are going to look at the third dimension, which is the standardization. Okay, also called Yokoten Kai. You can write this in Japanese if you want. You don't need to learn this, but just so that you have it. Wait. Yo ko ten kai. Okay, which means basically standardization. Okay, also just bring one process to the next factory, or bring one behavior just as the cpDNA to my people, and this is done through empowerment. As we have seen, this needs trust and the whole thing. Okay, Now we formalize all these concepts with a modelization, a mathematical model that helps us understand how this is being quantified. So we first make two assumptions, okay? The first one is that people, individual nodes in the network can be in two different states. S, susceptible, not yet infected. You can think about this as a virus, okay? Let's think about it. You want to implement a certain behavioral pattern in your organization, and some people are susceptible of being infected, and some are already infected with the behavior, okay? And so this is just the first case, okay? So this is the first approximation. And the second assumption is that each individual can infect anyone else. This is called the homogeneous mixing hypothesis. In reality, or HMH. HMH. In reality, this is not real because a leader has more potential of infection than a normal worker, HMH. Okay, this is our hypothesis. Okay. So, questions so far? So, the first make a first approximation to our Yoko Tenkai. Can be considered analogous to the so-called susceptible infectious susceptible model. This is also called SIS. In which we consider a behavioral pattern like a disease, okay, like a virus that spreads in a population in a network and, this is important, allow for individuals to forget, so people can forget what they've learned, the behavioral pattern and abandon it. Okay, so this is the first approximation. First you are susceptible, then you're infected, but then you turn again to be susceptible. So we have some parameters or variables. I of t represents the fraction of individuals who have been infected by the pattern. Okay. Beta is the rate of infection. K is the average network degree. Und mu times I of t is the forgetfulness rate at which the population unlearn the pattern. Then we can formulate following the variation of the fraction of individuals who have been infected by the pattern with time, or otherwise this means the speed of infection, is equal to beta times the rate of infection times the average network degree, how well are communicated the nodes, times the rate of infection, the fraction of individuals who have been infected, times 1 minus I of t. So this term is the infection, or otherwise learning of the pattern. Minus mu, the forgetfulness, times it, otherwise this is the forgetfulness rate. Forgetting. And that's why it's minus, okay? So solving this equation, this is a differential equation. We are not going to look into the solving of the differential equation, so you can skip that. The solution is, but you need to understand the solution, okay? This is the important. This is 1 minus mu divided by beta k times c times some exponential function. Exponential of beta k minus mu times t 1 plus c e times beta k minus mu times t. Okay, whereas c is I sub 0, I in t equals 0, divided by 1 I in t equals 0, so the rate in the beginning, multiplied by mu beta k. So this is a function of t. We are interested when t tends to infinite. So e when t equals infinite is the limit of e when t tends to infinite, equals 1 minus 1 divided by r0, where r0 is the reproductive number. Mid-COVID, with COVID, maybe you have heard of it, this R-Wert or R value. This is beta times k divided by mu. Well, this is important, the reproductive number, you need to understand, okay? If, what does this means? The upper value is talking about the infection rate, beta, and k is the connectivity. And mu is talking about the forgetfulness. So how people recover from the virus or from the disease, or forget the learning pattern. So if R0 is bigger than 1, then this means that beta k is bigger than mu, this means that we get infected faster than we forget, and this means that the virus, the behavioral pattern, spreads in the organization. If R0 is smaller than 1, this means that beta K is smaller than mu. This means that we get infected slower than we forget, and this means that the behavioral pattern dies out. Okay? Questions? This is just the same as with the COVID virus. So if R0 is very big, it's similar to say that beta is very big. The infection rate is high. If R0 is very big, it can mean that K is very big, meaning people are a lot in contact to each other. That's why if we want to bring the virus down, we either make the virus weaker with a vaccine, bringing beta down, or we let the people stay at home and bring the K down. If R0 is very big, this means that mu is very slow. People don't recover slowly from the disease. Okay? These are some explanations. Any questions, please? No questions? Okay, your call. Yes. So the second approach the second approximation takes place when individuals can only transmit the behavioral pattern to those they are in contact with. Okay. We know from statistics that the first momentum of a degree distribution is the average degree. And the second momentum is a measure of the heterogeneity. So this is just a standard deviation squared. Okay, for scale-free networks, have a second momentum tending to infinite. So the equation here is a little bit different as before. So we have some parameters. Let me explain the parameters first. Sorry. E sub k is the fraction of the nodes with degree k. That are infected among all other nodes with degree k. Degree k is the number of neighbors that a node has. And theta sub k represents the fraction of infected neighbors of a susceptible node with degree k. Okay. We can represent the differential equation. As I said, this is not relevant. Important is the interpretation of the solution. Okay, this is the differential equation. It's basically the same concept as before, but we have the learning on the right, on the left, and then we have the forgetfulness. Wait. If we solve this equation, we get that the condition for global spread of the behavioral trait is given when the characteristic time I explain what this means. To achieve 1 divided by E fraction of the population infected, tau, this is read tau, this is a Greek letter, is bigger than 0. Okay, and tau, and this is what is important for you, tau means the first momentum of the average distribution, the mean, divided by beta times the mean minus forgetfulness squared times the mean. This needs to be bigger than 0. Okay. So the condition, if tau is bigger than 0, this means that beta k squared is minus mu k is bigger than 0. Which means that the condition to predict if a behavioral pattern spreads on a certain organizational design is lambda equals beta divided by mu, being lambda the quote between the rate of infection and the rate of forgetfulness, needs to be bigger than k first momentum of the degree distribution divided by k squared. So this depends only on the organizational design. And this means lambda sub z. Okay? So what is the interpretation? High lambda means what? That either beta is high, so we have a high infection rate, or mu is low, so low forgetfulness. People remain infected long time. And this is the condition that the organizational culture transmits rapidly. If people are willing to learn, high infection rate, and people don't forget what they learn. Okay. Special case is a scale-free network. Because in the scale-free network, the standard deviation of the degree distribution tends to infinite, meaning that the behavioral pattern will always propagate successfully in the culture. Why? Because lambda equals beta divided by mu will always be bigger than k divided by something very big, being 0. Okay? So there is no opposition in scale-free networks. There is no opposition to spreading. Okay? This has to do with the nature of the network. Okay? Questions, please? Questions, please? Questions? So I guess this lecture is, I think, a little bit more difficult than the previous ones. That's why next week, wait, let me finish one moment, don't go. Don't go.